This is a video overview of Algebra 1 Lesson 9.1, where we'll just go over all the content below. So make sure you have your notes ready, and we're going to be talking about domain and range. So first, kind of an introduction problem, similar to problems you've seen before. So in class, we worked with many linear equations. We learned that these linear equations, they're just a type of function. So it's another equation. Most equations, they're just kind of another word for function. You can think of them fairly synonymously. We're going to learn a little bit of the difference, but functions were mathematical equations that when an independent variable was substituted in at any value, the dependent variable only had one solution. So another way to say that is every input has one output. And you'll notice from the activity this week, we'll be talking about inputs and outputs. So remember that the input values, which are typically represented by x, are the domain. They're what make up the domain. And the output values are what make up the range. That's an important thing to remember. So x is the domain values, and y represents the range values. One way I keep that straight, x comes before y in the alphabet, d also comes before r. So x and the domain go together, y and the range go together. So let's explore this idea with a few real-world scenarios. So many car rental agencies charge a daily rate to rent a car, as well as a small charge per mile above the mileage included in the basic fee. So suppose your family needs to rent a car. So that daily rate is $38. So no matter how many miles you drive, it's just $38. And then after the first 150 miles, it's 25 cents per mile. Okay. So let's kind of work at putting this into an equation. That's what we're going to do here below. So if you were to rent the car for one day, here's what your equation would look like. So x equals the number of miles driven over 150. So we have the 38 that you have to pay plus 25 cents times every mile that you drive. And that's going to give us our total cost. So now we want to know, what is the cost if your family drove 320 miles in one day? So we can use this formula above that we found. So we'll say, well, we know we drove 320 miles, but basically the first 150 don't count. So we'll just say, okay, let's do 320 minus 150 to find out how many miles we'll be charged for, which gives us this 170. And then we'll just solve this equation. So it's just like we're substituting it in. So 38 plus 0.25 times every one of those 170 miles given. We solve it, and so we find out our total cost will be $80.50 if we drive 320 miles. So in the case of this problem, the input value was x, or the miles driven. So the output value is the cost of renting the car for the day, which was $80.50. Notice there's only one input value you get for C if you put 170 in. So if you substitute 170 in, you're just going to get out $80.50. There's no other way to do this. You could never get any other value out for the output. This is an example of a function. So this is probably familiar. You've dealt with problems like this, and this is a function. So you're learning what you were already dealing with was also called a function. It's a relationship between two variables, an input and an output. This means there's only one output value possible for every input value. So one way I like to think of the input is it's the number that can change things. So the miles driven in this case is what's going to change the cost. That cost is dependent on the number of miles driven. So there are special names for the input and output values, like we've already mentioned. So the input values are called the domain, also the x values. The output values are called the range. And these terms correspond to a graph we'll look at below. In our soil problem, if we assume the company will only deliver soil in integer numbers, the domain would be all positive integers. In other words, all the values of the input could only be natural numbers, or like 1, 2, 3, 4, 5, because they can only deliver soil in integer numbers, or basically whole numbers. Okay? Sometimes there are situations where you may have the same input value though. So for example, if you compare the number of children in a class with the number of children who do their homework each day, the number of students enrolled each day would be the same, but the number of students who do their homework would vary day to day. So like there's always 20 students in the class, but the number who do their homework could change. So this one is not an example of a function. And do you know why? It's because these are repeated. Excuse me. So remember, if any member of this domain is repeated, the relationship is not a function. So this is a problem. Since those repeat, we know it's not a function. We cannot have repeating inputs or x values for it to be a function. You can have the range repeat. That's okay. We can have repeating in the range or the output, just not the domain. Notice how the members of the domain are all different. The range has some members that repeat. It's okay. The output values may repeat, but never the input values. So if that's one thing you remember, just no repeating input values. Okay, we're going to look at section 2. So identifying functions from graphs and tables. So we can express functions in many ways. This lesson will introduce you to 4 different ways to represent or identify a function. The first way you've already learned in section 1 is just the algebraic method. The second way is the vertical line test. And so we can see, we take a vertical line and we see, does this vertical line hit this function in more than one place? And as long as it doesn't, or sorry, this graph in more than one place, as long as it doesn't, it is a function. So what we're basically trying to decide is this graph a function? We do that vertical line test to check it. So notice on this graph, we have a bunch of vertical lines drawn. Well, you can see anywhere you draw these vertical lines, it will not hit the graph, the blue line, in more than one place. And so we know that graph then is a function. So that's another additional way to tell. Let's look at another example. So I want you to look at this and think, is this going to be a function? You might already see the writing. We'll hide that. So what do you think? Is this going to be a function? Well, it is not, and the reason is, if we do a vertical line right here, that vertical line is hitting this graph in 2 places. This vertical line is hitting the graph in 2 places, and so this graph is not going to be a function. Okay, so this is an example of a non-function. Now we can also look at a table to see if it is a function or not. So we make a heading for each column. We have the input and the output. I'm using that same equation that we started with. So just if we use some different inputs, 0, 1, 2, and 3. So if we substitute those in, we get these different values. So would this be an example of a function? Well, yes, we have all different inputs. All of those inputs give a different output. And so, yes, this would be a function. Okay, another way to see if it's a function is through mapping these relations. So mapping these is really similar to input-output tables. These might look kind of weird, but pretty much all you're doing is you're writing the numbers. So for example, if this was in a table, we'd have 2, 3, 5, 10, 16, and then we'd have 4, 1, 7, that is a 10, 2, and 8. So if this were in a table, this is what the table would read, okay? But this is just a different way of drawing it out. So you write all the numbers from least to greatest here, all the outputs from least to greatest here, and then just draw an arrow connecting them. And so what we can do is look, is there more than one arrow going from an input? If there's more than one arrow going from an input, it's not a function because that would mean a repeating input. So let's look at this one. We can see this one has 1 going to 1, 2 going to 5, 6 going to 4, and 6 is also going to 7, and 9 is going to 6. So think about this. Would this one be a function? What do you think? Well, hopefully you're saying no, we have a problem here. This 6 is mapping to 2 different numbers. So 6 is going to 4 and 6 is also going to 7. So this one is not a function. Okay, let's look at another one. So we have -4 going to 9, 3 going to 3, 7's also going to 3, 10 going to -2, and -12 going to 6. So I want you to think about this. Would this one be a function or no? So think about it for a minute. Pause if you need to. Well, if we look, the rule for it to be a function is we cannot have the input going to more than one output. And if you look, -4 is going to a number, 3 is going to a different number, 7 is going to a number, 10 is going to a number. What would be a problem is if we have 3 going to more than one number, but because, or any of these going to more than one number, because each of these inputs is going to a different number, or each of these inputs has exactly one number it's going to, this would be considered a function. So quick and easy way to look at it is you cannot have these arrows. You can't have two arrows coming off from one number. So you cannot have one number that goes to two different numbers. Each number just has to go to one number. So this one is, yes, this is a function because it's okay to have a repeating output, just not a repeating input. So let's look, can a relation have an input paired with two different outputs and still be a function? Think about that. Can we have that? So we have one relation, it has one input paired with two different outputs. Can that still be a function? Think about that. No, it cannot. This is an example of it. 6 has two different outputs, and this is not a function. Can a relation have multiple inputs paired with the same output and still be a function? Well, this last one is an example of that. Notice 3 and 7 both go to 3, but because each input is paired with just one, is going to a different output, none of the inputs go to multiple outputs, and so we're okay. So outputs can repeat, inputs cannot. Okay, I'm going to let you go ahead and watch this video to help you. This video might help you further with these, and then make sure you look at these two example problems. This will help you on the homework. If you're feeling confused, send me a message.